We're going to move on to the next speaker, and then we'll take questions at the end. And so our next speaker is Professor Bruce Clemens. He's a professor from Materials Science and Engineering at Stanford. And he will be talking today about solar energy and electrochemistry work that's going on at GCEP. He'll also tell us a little bit about a course he's been teaching and one of these massive online courses. So we look forward to his talk. So Bruce, once your computer's up, you can. The floor's yours.
Okay. I want to add my thanks to Reliance and GCEP for organizing this and inviting me to give a talk here today. And I'm going to talk about solar and solar photoelectrocatalysis as well. So I'm going to give you my take on it. Sally's introduced a lot of this topic already and a lot of the work that is going on in GCEP in this area. But I want to show you how I look at this. So here you can see circles, and the area of these circles represent the energy or power that we're getting currently from these technologies. And you can see that there's some bigger than others. Significant amounts of energy are being extracted from these places. Certainly the energy infrastructure is huge. However, if you look at solar, this is a pretty modest representation of what could be harvested from solar. Hitting 3% of the Earth's land harvested with 15% of efficiency. So that's just the land, and 3% of the land harvested with 15% of the efficiency, and it dwarfs all other energy sources that we're currently using. So if someone asks you what the energy source of the future is, you can confidently say it's solar. This is not distributed uniformly around the world, but you can see where I live in California, we have a pretty good solar resource, and India does as well. If I look at the U.S., which uses a profligate amount of energy per person, we have a good solar resource near high population density centers, which is a rare thing in the world, actually. And if we wanted to produce all our energy needs, not just our electricity, but all our energy with fairly low efficiency photovoltaics, we'd need an area about that big. So I put it in Arizona, which is a pretty sunny and hot place, and I figured the people there would appreciate the shade of the solar panels. And so if you work it out per person, U.S. uses about 11.3 kilowatts per person, which is a huge amount of energy, and we'd each need a photovoltaic array about 60 feet on a side to produce our energy. So the stuff had better be cheap and abundant. Just as an example of a photovoltaic array, currently this is on our house, I should say. My wife and I are both professors, and she also works in photovoltaics. So we're crazy enough to have put it on our house. And we produce more electricity than we use now. We're a net energy producer in our house. So let's talk a little bit about economics of photovoltaics and the issue of efficiency. So if you look at the life cycle cost of a photovoltaic energy, you can look at the price of electricity that you get from it, and you have the cost of the cell, plus the cost to balance a system, plus the cost of the installation in the numerator. And then in the denominator, you have the power that you get out, the power density from the sun, the efficiency, and the effective time fraction of time that you're at full solar power, and then the lifetime of the system. And so the important thing about this equation is that the cost of the cell goes here, so you can work on reducing this part of it as much as you want, and you'll still have these other two parts, the balance of system part and the installation part. Whereas if you work on the efficiency here, it divides all those costs. So the efficiency reduces the cost more than reducing the cost of the cell itself. So that's why GCEP is focused wisely on technologies that have the potential for enhancing the efficiency. So the cell cost includes cell material, manufacture, which can be high in cost and also high in energy content, and particularly for single crystal silicon solar cells or even multi-crystal silicon solar cells, where most of the high purity silicon that's manufactured for that process is lost in cutting the wafers. And certainly their wafers have to be much thicker than the solar cell aspect of it is required. The balance of systems cost includes encapsulation module wiring, the frame and mounting hardware, stuff that's hard to make cheaper, and the installation cost includes labor for installation and maintenance, etc. So with our system, those were each about $1 a watt. The cost of the cell is only one component, so even with free solar cells, the electricity would not be free, so that's the point. And the efficiency, lifetime, and the sunshine drive all costs, which is means that if you're going to spend the world's resources in making solar cells, you want to put them in a place where they get a lot of sun, which is what always bothered me about the German incentives, because Germany has the solar resource of Alaska, and it's still, if you put a lot of solar cells there. I want to talk just a little bit about how a solar cell works. It's made up of something called a conductor, which has a band gap, which is a region in energy where there's no electron states. And so you have a band that's nearly full of electrons and one that's nearly empty of electrons, known as the valence and the conduction band, respectively. And light kicks electrons from one band to the other. And then you harvest those electrons, and the hole that's left behind is energy. So you can hit it with higher energy light, and you get a big excitation from deep in the valence band to high in the conduction band, and lower energy light, and that's less, and you get an even lower energy light, and they're even closer to the bands. If you get low enough energy light, you don't have enough energy to kick the electron from the valence to the conduction band. But what happens immediately is you lose that extra energy, because the hole relaxes up towards the top of the valence band and the electron relaxes down towards the bottom of the conduction band. So any extra energy that photon had above the band gap energy, you lose with a single junction solar cell. So, and you also lose all the photons which don't have enough energy to excite an electron from the valence band to the conduction band. So those are two big losses that you have in a solar cell, and that greatly limits the efficiency that you can get from a solar cell. And people have looked at this some time ago. Shockley and Quasar is a famous paper, and they've calculated using a detailed thermodynamic balance what efficiency you can get from a single junction solar cell. And here it is plotted as a function of the band gap, and you can see it peaks at a band gap of about 1.4 eV, and it peaks about 30-something%. So that's as good as you can ever do with a single junction solar cell. So there's two approaches that GCEP is using to try to get high efficiency, and one is to come as close as possible to that theoretical value in inexpensive solar cells, and the other one is to exceed this limit by trying new approaches that aren't just single junction solar cells. So Sally showed you this picture, and just for clarity, I'm talking about this wedge of the pie that talks about photovoltaics. And here's some of the projects you've seen already. Sally talked about them. This is in organic PV. They have a lot of potential because they could be made inexpensive, and if you could tune the molecules, they could potentially be made efficient as well. Sally also talked about this work involving nanoparticles. This one is an interesting one. You have light coming in causing heat, so you have a broadband absorption, and then a re-emission into a narrow band. And then you can have your semiconductor so that the light that's emitted has just enough energy to excite a carrier from the valence to the conduction band, so you don't lose so much in that relaxation process. And then she also mentioned the recent demonstration of an all-carbon-based solar cell, keeping Earth-abundant materials. So This is another approach here for beating the Shockley-Quasar limit, where you avoid the relaxation process in both the valence and the conduction band, and you develop a population of electrons in holes as a function of their energy, and you have selective contacts that just pull out from one particular energy that then gets repopulated in the valence and conduction band by electron-electron scattering without any electron-photon scattering, so you avoid losing that extra energy. This is a project that she also mentioned. If you can reduce the amount of material in the solar cell by enhancing the absorption with various effects, you can reduce the cost of the solar cell and still have very high efficiency. This is a completely new approach that's based on photon-enhanced thermionic emission. So this is a solar cell that works better when it gets hot. It turns out one of the sad things about solar cells is you put them out in the sun and they warm up, and when they warm up, they work worse. The efficiency drops when they get hotter. But with this photon-enhanced, it works better when it gets hotter. So this could be combined with a thermal capture, energy capture system in order to increase the efficiency of the whole system. And then she also mentioned this work on solar fuels where they're looking at making both anodes and cathodes with a very clever nanostructure or microstructure, and I should say, approach to material fabrication. So now I'll turn to some of our work that was actually started in a GCEP project, but is now transitioned to a consortium involving several companies called the Bay Area Photovoltaics Consortium. And this work is in the area of using earth-abundant, non-toxic elements to make a new material. And the material we're looking at it's called CZTS. I hate that name because it uses T for 10, and everyone, the symbol for 10 should be S, but anyhow, at least if you're going to shorten it. In any case, it has potential. It's got the band gap right where it should be for high efficiency, 1.45 eV. There's no reason why we shouldn't be able to make a 25% cell with this material, but no one has yet. It's earth abundant, and the cost for the materials is low. Our work has developed new ways to process this material that are more scalable than the world record approaches. These world record approaches involve explosive materials, hydrazine, in fact, in order to make it, and it's not considered to be large-scale manufacturable, whereas we've done it with this sputter deposition and nearly reached their record, but it's still not good enough, and we're looking more deeply into why we're not doing better. But we've created a lot of excitement about this material, and if you look at the number of papers per year about this material, it's jumped up dramatically. The last thing I'll talk about in terms of our work is it's a technique for making single crystal materials with a thin film process that doesn't consume a single crystal substrate. And this is a spatially engineered delamination layer. And what we do is we grow with epitaxial growth on a single crystal substrate, but we first put a mechanically weak layer, and then we grow the epitaxial semiconductor on top of that. And then we can bond glass to it, peel it off, and then we have this thin film, high quality material on a cheap substrate. And we can, in fact, do the whole processing of the device before we pop it off, and then pop it off, we have the complete device on a cheap substrate. So we've demonstrated this already in terms of getting single crystal silicon films. This is a picture of some of them that have popped off the substrate. So the last thing I want to talk about is my class. I've taught for some years a class called Solar Cells, Fuel Cells, and Batteries, Materials for the Energy Solution. And I have a huge range of students in this class, and I always felt that there was about half the students lost and half the students bored, and maybe for one student the class was just right. And so I decided to record my lectures so that they could watch them at their leisure, rewatch them if they needed to, and watch TV while they're watching them if they didn't. And so I did problem sets online. And so I did this new flipped classroom, which allowed me to offer it free to the world. as a massively open online course. And I did so last fall, and I will do so again next fall. So I post recorded lectures. I used a low-cost, low-production value, short segment lecture format. I had online homework and final exams. I had a very active forum for the online students. They took a lot of interest in the forum, and they put a lot of effort into their presence on the forum. I had over 12,000 students sign up for this course. The Stanford students did get more for all the money they paid for it. We did a lot of extra things for them, including a lab, problem sessions, question and answer sessions, and so forth. So just a little bit about it. I had 12,400 sign up, only 383 completed. My hat's off to those people who sat through all my lectures. Here's a distribution of the ages. I had a 10-year-old complete the class, which I find frightening that there's a 10-year-old somewhere that was integrating the density of states times the Fermi-Dirac distribution function to find the electron concentration in the conduction band in semiconductors. I did have participation from many countries around the world, and you'll notice that India is pretty high up there. This is my first trip to India, but according to this, I've already been in India about 8,000 times. So I will be offering it again in the fall of 2013, and it will be offered through Stanford and the edX platform, free to anybody, anywhere. Sign up online. This was the sign up for last year. I'm not sure it'll be the same for this year. Just to finish off with a lecture, let's see. Solar cell, which is a p-n junction made of semiconductors of p-type and n-type joined together
low production
with a
value
photon
done just in
that
my
creates
office
an
at
electron and
Stanford.
hole, in this case in the p-type region. The electron is unhappy there, and it looks over and sees, hey, I could lower my energy considerably by drifting over here to the n-type region. And so it does so. And that's current through voltage.
You can see that would get old listening to that. So I tried to liven them up a little bit by having some humorous things in the beginning of my talk. So here's one where I did so. Let's see. Did you turn off? Oh, sorry. Yeah, I need the audio back on. Sorry. You can see I survived the horrific bike accident, and I go on to give the lecture. So, thank you again. This has been a fantastic trip. We were welcomed with open arms into a village. We listened while people shared their hopes. We saw people building for their future, and we saw beautiful gourds filled with seeds for a better future.